So we are doing problems from chapter 17. Okay, so this problem says the displacement of an air molecule in sound wave is modeled with this function. Okay. What is the wave speed? What is the maximum speed of the air molecules and so on? So we're finding a whole bunch of stuff. All right, and let me show you what this thing is telling you. Okay, you saw that. Okay, maybe I still have a. So you saw that this is a sound wave going through air, okay? And there is that molecule, each molecule, the red molecule that's oscillating parallel to the direction of wave travel. And so its equilibrium position is S equal to 0. And that's what that function is. It's giving you the oscillation of that red molecule, okay? So that's what this is, okay? So let's write this down. Sxt equal to 5 nanometer. Cosine. All right, well, I'll first write the general form. It's the amplitude cosine kx minus omega t. So for our sound wave, it is 5 nanometer cosine 91.54 x minus 3.14 into 10 to the 4 t. And I didn't write down units. Everything is in SI units. This is in meters, and so this is inverse meters, because this phase is dimensionless. Okay, this quantity is dimensionless. So this is in seconds. That means this guy is in inverse seconds. Okay. All right. There's the amplitude of the wave, the amplitude of the oscillation of the air part molecules, and you see there that's the amplitude is 5 nanometers. Okay. The size of an atom is 1/10 of a nanometer. So this is roughly 50 atoms width. Okay. So if the size of my fist is an atom, it's oscillating like that. Okay. And it turns out that if you refer to your notes, the softest sound you can hear, the amplitude is 1/10 of an atom. So this is a very loud sound. Okay. Anyway, so that's what that is. Okay, they ask you what is the wave speed. They're asking you what is the They're asking you what is the speed of the wave. Okay. So we'll refer to two different things: the speed of the wave, and then we'll also talk about the speed of the air molecule. Okay. So you understand that this speed, the maximum speed, that's like a mass attached to a spring. That speed can be a lot greater than the speed of the wave. Okay. So, I mean, that speed is also very different. So what is the wave speed of the sound wave? The wave speed is frequency times wavelength, which is omega divided by k. Okay, so omega is 3.14 into 10 to the 4 inverse second inverse meter. So this works out to 343.2 meters per second. So that is the speed of sound in air at about 20 degrees Celsius, okay, which is the temperature in this room right now. So at this temperature, that's the speed of the sound. So what is the maximum speed of air molecules? Okay. Now remember, this is the displacement of the air molecule that you saw in the simulation. And for a spring, for a mass attached to a spring, when is it going the fastest? So, have this in your mind, in the back of your mind. So here's this is executing simple harmonic motion. When is this going the fastest? At equilibrium, okay? And so those air molecules are also executing simple harmonic motion, and they'll be going fastest at the center. But so the speed of the air molecules, so the speed of the particle, this is the speed of the wave. The speed of the air, the particle is delta S, its displacement as a function of time. Okay? And we had to take the partial derivative because that displacement is a function of both position and time. Different particles at different points are under, their displacement is different. Okay. All right. How do you take a partial derivative? What is taking? Yeah. Very good. Okay. So you're treating x as constant. So I'll first write down the general formula, and derivative of cosine is negative sine, and you're taking a partial derivative with respect to t, so you'll get a minus omega. So this is equal to a omega sine kx minus omega t. Okay. And what you want is the maximum value. Okay, what is the maximum speed? The maximum speed happens, okay, these two are constant, so maximum speed happens when this is 1. Okay, so Vp max is a omega, and the amplitude is 5 nanometers, and omega was 3.14 into 10 to the power 4 inverse seconds. Nanometer is 10 to the minus 9 meters, and 3.14 is pi into 10 to the power of 4. And what we'll do is we'll make this 10 minus 6, so 50 pi micrometers per second. A micrometer is roughly the size of a cell. Okay. 157 micrometers per second, or 0.157 millimeters per second. Okay, so you've seen a millimeter, and this is a tenth of a millimeter per second. Okay. That's how fast the molecule is going at its fastest, okay, which happens at the center. Okay. And then they ask you, what is the magnitude of the maximum acceleration? Okay. So a mass attached to a spring, where is its acceleration maximum? What's that? At the extreme points. That's where the force is the greatest and the acceleration is the greatest. Okay, how do you get the acceleration? Acceleration is the second time derivative of that. Yeah. Okay, so you're taking the time derivative of this. Time derivative of sine is cosine, and then you get a minus omega. So it's minus a omega square cosine kx minus omega t. And we want the maximum value. So this is, by the way, for the particle. So okay. So this is again a omega. We just found that in the last slide. That was the maximum velocity times omega. So we'll put that in there. 50 pi, 55 pi and then omega is pi times 10 to the power of 4 per second. And this works out too. So the maximum acceleration of the particle is 4.9 meters per second square. Does this number ring a bell? Yeah, exactly, half of gravity. What does that mean? What that means is when the particle is there at the extreme point, the force, the restoring force on it is half its weight. Okay. And how's that force coming about, roughly? Okay. So when it's here, when it's in the peak of the pressure and there's vacuum there, it gets pushed from high pressure to low pressure region. Okay. So that, okay. Anyway, that's just roughly, loosely speaking, but that's what that is. All right, so bats use sound waves to catch insects. Okay, so here's how your ultrasonic sensor works. So here's a bat. So it wants to see this stuff. What does it do? The bat sends out sound waves, ultrasonic waves. These sound waves are reflected back, okay? And the bat has 3 pieces of information. What are the 3 pieces of information? So the sound wave reflects back. The time delay tells it how far away the insect is. The intensity of the reflection tells us the size of the object. And the frequency shift, if the reflected wave has a higher frequency than that means this object is coming toward the bat. And if the reflected wave has a frequency less than the emitted frequency, that means this guy is moving away from the bat. So it has these 3 pieces of information: the time delay, the intensity of reflection, and the frequency shift. Okay. If you watch some nature shows, bats will fly out of a the darkness doesn't matter, out of a cave with all kinds of branches at about 60 miles an hour. So it's processing all that information super fast. Okay. All right. So bats use sound waves to catch insects. Bats can detect frequencies up to 100 kilohertz. Okay. What is the range you can listen to? You can hear? What is the range in which your sensor works? 20,000. Yeah. Okay. So that's why this is called an ultrasonic wave. You can't hear it. Okay. But if the sound wave travels through air at a speed of 343 meters per second, what is the wavelength of this sound wave? Okay. So the problem itself is fairly simple. But the implications are pretty interesting. Okay, so 343 meters per second, and frequency is 10 to the power of 5 per second. So it's 3.43 into 10 to the minus 3 meters, 3.43 millimeters. Okay, that's the wavelength of the sound. Okay, so here's what this means. Okay. So if you use see, how do we see stuff? How do you see stuff? I'm sorry? Yeah, so light falls on something and then it's reflected and you see the reflected light. Okay, so if you're using a wavelength like this, the smallest object you can see is this, that size of the wavelength. Okay, so D is roughly the size of the wavelength. So if you had a smaller object and you use a wavelength like that, you can't see this guy. Okay, so you can't see this guy. All right, so here is a bat using a 4 millimeter wavelength. So that's the smallest bug it can see. So if a bug is smaller than 4 millimeters, it can't see it. Okay, so you see, if another bat uses a higher frequency sound, ultrasonic wave, it could see the smaller bug, and it wouldn't be impinging on this guy's territory. So you can have different bats living in the same area. All you have to do is use different frequencies. Okay? And in fact, in nature, that does happen. Okay? So the bats that eat big bugs are big, and the bats that eat tiny bugs are tiny. Yeah? Well, anyway, so what we're saying is you use different frequencies. Bats using different frequencies can live in the same area. So this says, what is the speed of sound in a medium where 100 kilohertz frequency produces a 5.96 centimeter wavelength? Okay, so this frequency is the same as in the previous problem, except that the wavelength is much higher than this. This is millimeters, and that is centimeters. Okay, so roughly 10 times greater. So the speed has got to be 10 times greater. Okay, so again, the speed is centimeters, 10 minus 2 meters. Okay, so that's 10 to the 3, and so 5,960 meters per second. And here's a table, and you see this sound wave is traveling through steel. That's the speed of sound in steel. All right, this problem says the density of a sample of water is 1,000 kg per meter cube, and the bulk modulus is that what is the speed of sound through water? Uh, if you look up your notes, the speed in a medium is the elastic moduli divided by the inertial quantity. Okay, so here the relevant quantity is the elastic modulus is bulk modulus, and the inertial quantity is the density of the medium. So let's put those values in. 2.15 gigapascals. That's 10 to the power of 9 pascals. And the density is 998 kilograms per meter cube. Okay, so what we'll do is we'll make this 0.998 times 10 to the 3. That becomes 10 to the 6. Square root of that is, that'll give you 10 to the 3 outside. 10 to the 3 meters per second. And 2.15 divided by 0.998. So the speed is 1,468 meters per second. So that's the speed of sound in water, 1,500 meters per second. And you see, there it is. So okay. Okay, so they tell you that the lawnmower makes a sound, its sound level is at 91 decibels, and you want to calculate the intensity, okay, of the sound. So your sense of loudness responds to that, but an electronic instrument would measure the intensity, okay? And then you can convert that to decibels. But okay, let's find that. Okay, the decibel level is given by this formula: 10 times log intensity of the sound divided by I naught. I naught is the threshold of hearing, and I naught is 10 to the minus 12 watts per meter squared. Okay. Do you guys know what is the frequency that you hear the best? The softest sound? 3,500 hertz. Okay. All right. So the sound level is 91 decibels equal to 10 log I by I naught. Okay. So 9.1 is log I by I naught. Okay. And so if you want to get rid of this, okay, so 10 to the power 9.1 is equal to 10 to the power. Okay. Log of a number raised to the power 10 gives you that number back. Okay. So I is equal to okay, so that's the intensity of the sound. 91 decibel sound has an intensity of 10 to the power of minus 2.9 watt per meter squared. Okay? And if you want to get a decibel number, uh, uh, and so this is equal to 1.26 into 10 minus 3 watts per meter squared. So 1.25 milliwatts. Okay. All right, this problem says an 8-hour exposure to a sound intensity level of 90 decibels can cause hearing damage. What energy in joules falls on a 0.8 centimeter diameter eardrum to so exposed? Okay, so it's a 90 decibel sound. Okay, so from the decibel level, we'll calculate the intensity, and from the intensity, we'll calculate the energy falling on the eardrum. All right, so this is 90 decibels. So we've been through this one calculation before. 9 equal to log I over I naught. So 10 to the 9 is I over I naught. I is I naught. So the intensity of sound falling on the eardrum is watt meter squared. Okay, so from the decibel level, we've gotten that. Okay. Now, intensity is power per unit area. So energy over time times the area. So the total amount of energy falling in an 8-hour period is the intensity times the time times the area of the eardrum. Yep. So this is 10 minus 3 watts per meter square. The time was 8 hours, and 1 hour is 3,600 seconds. And the area is pi r square, and it's an 8 centimeter diameter, so 0.4 centimeters centimeters 10 to the minus 2 meters. Yep. Yep. So that's how much energy has fallen on the eardrum over a period of 8 hours, and that can cause hearing ear damage. Okay, so that can cause hearing damage. Okay, let's take care of powers of 10. We'll make this 10 to the power 3. That kills that. That's 10 to the minus 4. Well, we'll make it 10 to the minus 3, 10 to the minus 6, 4 squared. Okay, so the energy falling so that's equal to 8 times 3.6 times pi, 8 times 3.6 times pi times and we had 4 squares, 16. and that'll come out in joules. So let me make sure of. Oh, I forgot the 10 to the minus 6. Okay. So, right, there's a 10 to the minus 6 from here, and that became 4 square 16. So I made the 4 times 10 to the minus 3. And then squared that, that becomes 10 to the minus 6. So this is 1.45 into 10 to the minus 3 joules. Okay, so if this much energy fell on your ears, it could cause hearing damage. Okay, so I mean, this is a number. Let's see how to get a sense for this number. Okay. Yeah. If you take an object like this and drop it, how much energy does it have? It has mgh. H is the height from which you drop it. Okay. So let's say, well, g is 10, and this is 1 meter. Okay. So if you drop 1 kg from 1 meter height, so 1 meter is this height, and can you? Oh, yeah. If you drop this water filled from that height, you would have 1 kg, 10 joules of energy. Okay. Well, we want that much joules, so instead of dropping this, now we'll drop 1 gram, and so 1 gram would give you, if you drop 1 gram from 1 meter, it'll give you 10 to the minus 3 joules of energy. Oh, no, it'll give you 10 millijoules. So this much energy is if you drop 1 gram from a height of 0.1 meters, from a height of 10 centimeters. So you've seen in chemistry the 1 gram piece. If you drop it from this height, that hits your eardrum. That's the amount of, yeah. Okay. All right. Do you guys remember what is the efficiency of a speaker? 1%. What does that mean? If you have 100 watts speaker, that's the amount of electricity it's using, 100 joules per second. It's converting 1 watt of that to sound. Okay. Anyway, loudspeakers can produce intense sounds with surprisingly small energy input in spite of their low efficiencies. Calculate the power input needed to produce a 90 decibel sound for a 12 centimeter diameter speaker, so 1 foot diameter speaker. That has an efficiency of 1%. Okay. So this value is the sound intensity right at the speaker. So you saw that. Okay. So we have the decibel sound level, and from there you can calculate the intensity. We've already done this calculation. So for 90 decibel I naught, I works out to 10 to the minus 3 watts per meters square. Okay, see, we did this calculation right here. 90 decibel, there's the intensity. All right, so that's the intensity at the speaker. What we've calculated is, so here's the speaker, and right here the intensity is that. Now, you know, a speaker, if it sent out the sound perpendicular to the speaker, the sound spreads out, so as you go further, this intensity will drop. But this is the intensity right at the speaker. Okay. Well, what is intensity? It is power divided by area. Okay. And so the power of the sound, the energy put in is intensity times area. And the intensity is 10 minus 3 watts per meter square. And the area is pi r square, 12 centimeter diameter, which is, so that's 6 centimeters is the radius. Square. So the power in the sound wave, the energy in the sound wave per second is this. And this is 10 to the minus 4. That makes it 10 to the minus 7. Power is watts. And then pi into 36. All right, so this works out too. .3 into 10 to the minus 6 watts. Okay, so that's the power of the sound. Okay, and what is the speaker efficiency? For 100 watts of electricity, you're getting 1 watt of sound. Okay, so when you go buy a speaker, the wattage that they tell you is how much electricity it's using, not, okay, so the power of the speaker is power of the sound times 100. Okay, it's 100 times. Okay. So it is 11.3 into 10 to the minus 6 watts times 100. So a milliwatt speaker, 1 milliwatt speaker, if you put your ears right next to it, you get a 90 decibel sound. Okay, that's what that is saying, a milliwatt speaker. Okay. This problem says, what is the fundamental frequency of a 0.672 meter long tube open at both ends on a day when the speed of sound is 344 meters per second? What is the frequency of its second harmonic? Okay, so the fundamental frequency of a long tube open at both ends, so this is the lowest mode of vibration. Okay. You have antinodes at the end and a node at the so no, a node in the middle and an anti-nodes at the end. Okay, so to complete this wavelength, you'd go like that. So that would be the wavelength. So this is half the wavelength. Okay, so L. So for the fundamental node, this is half the wavelength. Okay, so the wavelength of the sound that is excited is 2 times L, and so the frequency is speed times the wavelength, and the speed is so the speed of sound in air that day is at that temperature is 344 meters per second, and the wavelength of this sound that is excited, the lowest frequency sound that's excited, is 2L, which is 2 times 0.672 meters. So this is 2 feet. Okay, that's 60 centimeters, a little over 60 centimeters. Okay, so the lowest frequency, we'll call it the we'll call it 256 hertz. Yep. And then they ask you what is the frequency of its second harmonic. Its second harmonic is 2 times that. The second harmonic would correspond to this. Okay. Yeah. So it's got a complete wavelength. Yeah. And you can look up the formulas. F2 for a pipe open at both ends, it's N times F1. So F2 is 2 times F1, 512 hertz. So this problem says a piano tuner uses a 512 hertz tuning fork to tune a piano. He strikes the fork and hits a key on the piano and hears a beat frequency of 5 hertz. Okay. So when he hits a key on the piano, that plays a frequency and the tuning fork is that. And he hears a 5 hertz beat. So that means when he hits the key, that piano key is playing either 5 hertz less than this or 5 hertz greater than that. Okay, when you play two frequencies simultaneously that are different, the beat frequency is F1 minus F2, the difference, the absolute value of the difference. Okay. So when he strikes the piano key, so the frequency of the piano is either 512 minus 5, which is 507 hertz, or 517 hertz. Okay. All right. Then he does the following. He tightens the string of the piano. Okay, you guys remember the velocity of a wave on a string is tension divided by mu. Okay, so when he tightens the string on the piano, he's increasing the tension. He's increasing the speed. The wavelength depends on the length of the string, so he hasn't changed the length. So when you increase the tension, what you have done is you've increased the pitch of the string. You've increased the frequency. He tightens the string of the piano and repeats the procedure. He once again hears a beat, the beat frequency of 5 hertz. So initially it must have been that, and when he tightened the string, it went to 517 hertz. So that's what happened. So initially the frequency was 512 hertz. He tightened the string, and the beat frequency went, and the frequency of the piano went up to 570. So the guy is tuning the piano, so now he's got to loosen it and so on. Okay. Oh, it went from 507 to 570. Okay. All right, so here's a Doppler effect problem. At an air show, a jet flies directly towards the stands at a speed of 1200 kilometers per hour, emitting a frequency of 3500 hertz on a day when the speed of sound is 342 meters per second. What is the frequency? What frequency is received by the observer? What frequency do they receive as the plane flies away? Okay, so now let's find the speed of the source. It's 1200 kilometers per hour, and so this is 1200. A kilometer is 10 to the 3 meters, and 1 hour is 3600 seconds. Okay. So we are converting that to meters per second. Okay, so the jet is flying just under the speed of sound. Okay, so it's not breaking this sound barrier, and that's good, because if it broke the sound barrier and it flies close by you, everybody in stand would go deaf probably. Okay, from the shock wave. So what is the frequency you hear? So this is the observer, and here's the source. When it's coming toward you, the frequency you hear is V plus V0. So again, you could look this formula up in the notes. This is the observer speed, this is the source speed, and these guys are positive when they approach each other. So in this case, the observer is at rest, so this is 0, and the source is approaching the observer, so that's positive. Okay, so F prime, and V is the speed of sound. So that's 343 plus 0, that's 343 minus 333. Okay, I'll just say 333, okay, times F. So that's 3,430 times F. Oh, no, that's, I'm sorry. So this is 34.3. That is 10. 343 divided by 10 is 0.0 So the frequency received by the observers is 120,000 hertz. Can you hear this sound? No? Right, but can you hear a plane coming at you? So what is happening? Can you hear a jet coming at you? Okay, every frequency gets increased by that factor when a plane is flying like that. So it's the low frequency that are produced that come into your hearing range. Okay? And so let's figure that out. So what is the highest you can hear? 20,000 hertz. We'll divide 20,000 by that. Okay? And any frequency less than that you can hear. Okay, so 20,000 divided by 35 is 570 hertz. So any sound that the plane produces whose frequency is less than 570 hertz, that will be in your hearing range. Any frequency that is higher than 570 hertz, that will be out of your hearing range. Okay. Okay, so when the plane flies directly away, so now again the observer is at rest and the source is flying away. Okay, so when the source is flying away, that velocity is taken to be negative. So 343 divided by 343 minus of minus 333. Okay. Okay, so now the frequency you hear as the plane is flying away, the frequency you hear is half the frequency that is emitted. Okay, so since your range is, so now this plane, as long as it's producing a frequency less than 40,000 hertz, you can hear all of that. Okay? Between what it produces between 40,000 and 40 hertz, you can hear. Okay? In this case, for this case, the frequency had to be less than 570 hertz for you to hear it. And in this case, the frequency produced had to be between 40,000 hertz and 40 hertz. Okay. So that's what's going on. Okay. So these frequencies that the plane produces are Doppler shifted into your hearing range. And when it's flying towards you, these frequencies are Doppler shifted into your hearing range. Yeah. All right, last problem. Airplane moves at Mach 1.2. What does Mach 1.2 mean? That's right, okay. And produces a shock wave. What is the speed of the plane in meters per second? What is the angle of the shock wave? Okay, so so Mach number is given by speed of sound divided by the speed of the source. Okay. And so 1.2 is V over V source. the other way. And the speed of sound is 340 meters per second. That's what we'll take. So the speed of the plane is 340, 20 times that is 68, so 408 meters per second. Okay. And then in part B, they want you to find the shock angle. They want you to find that angle. And if you look up your notes, the sine of that angle is given by, okay, again, the way to remember this is, see, this has a solution when the source is flying faster than the speed of the sound, okay? So theta is sine inverse of V over V source. And the source is flying 1.2 times that, so theta is sine inverse of 1 over 1.2. Okay, so what this problem tells you is, if you look at a supersonic flight, you'll see that clouds condense like that, and from this angle, you can calculate the speed of, if you know this angle, then you can calculate how fast the plane is flying. Okay? All right, guys, that finishes the problems.